Hello. Hi. How are you doing today? I'm so thankful. Yeah. Yeah, one day I had 3 classes, two recitations and 2 class. Even though they're shorter, but still one after another, one after the morning. How everyone is doing today? Yeah. How are your weekends? Too short. Our time is flying so fast. I feel like I don't have time to do anything. Once I start doing something, I'm still doing the thing, but 3 hours, 4 hours already passed. So weird. Did you guys notice that I actually extended homework 1 to 4 for 2 more days? Make sure it is finished before the new deadline. And then you have the whole semester all done. One day. I spent like 7 hours on Saturday. Wow. Then you have the whole semester to do the rest of the homework. So you can do them slowly. But don't wait for the last minute to do all the homework and then ask me for extension. I don't want to give you another extension because I need the whole semester to do all the homework. So do them, make sure you do them little by little. And if you need to do everything together, no problem. Go for it. So does anybody have any questions from anywhere in general? No. Okay, I think I should tell you something which I did not realize before until I forgot who emailed me. Yeah, this sunshine. If you love your smartphone, you're not alone. Half of the boomers living in their island and armland, and then took part of this group, blah 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 blah. So when I did this question in class, I said these two cards and half represent sample. Actually, no, they represent population. So half of the boomers. So if boomers means the population, half of the boomers means half of the population. Okay? And then 50 to 64 age group, it represents the whole population of this group. So 2/3 of this group means 2/3 of the whole population. So these two numbers don't represent samples, they actually represent. Okay. Hey, last one we started probability. Probability is fun to understand. It's annoying if you don't. And I'm in the second group. I don't understand it much. So I hate probability. Why I don't understand? Because we can do same question in so many ways. You can think in so many different ways, and you can do in so many different ways. But like math, you can do many ways, but the result should be same. In probability, it's not the same. If you do it differently, then the result is completely different than what the actual result should be. Just complicated. Okay? But anyway, I collected fun examples and easy examples for this. Okay? So you don't have to hate me as much as I hate it. So I'll try to make it like easier and I'll try to teach in simpler way. Okay? But if you already know more simpler way of understanding them, feel free to use your own method to understand. Okay, so we said experiment is a process that results in one and only one of the observations, and outcome is what we get from all those observations. So in all those experiments, sample space is collection of all those observations. Okay, and event is any collection of all the observations we get from, or the outcomes we get from the sample space. And we have three ways of doing probability: classical, relative frequency, subjective. Subjective means you are guessing, educated guess. Okay, you're not doing any math. Usually, you're just thinking. Relative frequency based on the frequency, so you'll be given a table of frequency, and then you're just going to use the numbers from the table to get the probability. And the most uncertain one is the classical one. You have to think logically what is given, what we are asking for, all these things. So the harder one is the classical one. And we started the classical one, and we said to find probability of any event is number of favorable outcome we have divided by all things we have in our sample space, total number of outcomes we have in the sample space. For example, if you roll a die once, there are 6 possible choices we have, number 1 to number 6. And if you are going to pick any number, let's say I pick number 2, we can have 2 only once in out of 6 times. So that's why it's 1 out of 6. So how many times you can get something divided by total of outcomes, total possible outcome from that sample space. And then the last thing we talked about is how can you use tree diagram to figure out some types of results from inequality. Like here we work with flipping a coin twice, and when you draw the tree diagram, first we start flipping and you have 2 choices, head or tail. Once we have our first choice, then we flip again. So each flipping has 2 more choices again. And we collect all those outcomes by reading our branches. So we collect all the letters from each branch, we put them together. Those are the sample spaces we have, all possible outcomes. And now we are going to start today's lecture by doing the same thing, but this time we are flipping the coins 3 times and see what happens this time. Oops. So if you observe, you see that let me erase this. You can see the outcomes we have for the 2 trial is head-head. This is head-tail. This is tail-head. And this is tail-tail. So we flipped twice. And how many outcomes we have in our sample space? 4. Now we are flipping 3 times, and you're going to see how many outcomes we get when you flip it. So head or tail, then again either head or tail, head or tail. So this is flipping 1, this is flipping 2, and now we are flipping for the 3rd time. So this is flipping for the 3rd time. And we have again. Thank you. See, I said I was sleeping. I really am. This is actually. So head, tail, head, tail, head, tail, head, tail. Now to see the outcome, you just follow your branches. We have head, head, head. Then the next branch, head, head, tail. The following branch, head, tail, head, and I'm too tired. You tell me. All right. What's the next one? Head, tail, tail. Next. Tail, head, head. Tail, head, tail. Please close all the laptops. The next one. Tail, tail, head, and finally tail, tail, tail. So total, how many outcomes we have? 8. So when you flipped it twice, we got 4. When you flipped it 3, we got an 8. Can you guess if you flip it 4 times, how many outcomes you're gonna get? How do you know? How did you figure that out? True. This is 2 square. This is 2 cube. So whatever times you're flipping, it's 2 to that. So our next one should be 2 to the 4, which is 16. So what's the observation you make? Depends on how many outcomes you can get from each trial. So from one trial, there's only 2 outcomes, either head or tail. So we have only 2 possible outcomes. And then depending on how many times you are doing the same experiment, you can use that number. If you flip it twice, it's 2 squared. If you flip it 3 times, it's 3 squared. If you flip it 100 times, it's 2 to the 100. So number of outcomes is the base, and how many times you are doing a trial, it's M. And when you roll it like 6 times, each experiment has only 6 choices. So depending on how many times you want to do your trial, it will be 6 to that number. So if you do it twice, if you roll it like twice, it's 6 squared. If you do it 50 times, it will be 6 to the 54. Okay? So that's the general rule. The denominator for our probability we get using this rule. It's whatever number of outcomes we have to the power how many times you are doing the trial. Okay, let's do some fun example. You are rolling a die once. Okay, only once. What is the probability of getting the following things? What is the probability of getting an even number? 50%. How do you know? So we have 3 events out of total how many? 6. 1/2. That is 50%. So when you roll a die, our sample space is 1, 2, 3, 4, 5, 6. Half of them are even, half of them are odd. So what's the probability of having an odd number? Another 50%. Because of the same rule, it's 3 out of 6. We have 3 odd numbers out of those 6 choices. How about getting a 4? 10%, how did you figure that out? What over what? 1 out of 6. Is it 10%? No, it's more than 10%, I think. Yeah. If you have 10 numbers, then probably it's 1 out of 10, it's 10%. It's 1 out of 6. But your idea is okay. You got the idea. More. Who wants to do D? Getting a number bigger than 5. So we have total 6 numbers in our sample space. How many numbers more than 4? 2. 5 and 6, right? So 2 out of 6, 1/3. And if you want to use percentage, it's 30, about 33%. Interesting one. Who wants to try the next one? Why it's 0? Exactly. Don't get anything bigger than 6 in our sample space. 0. So it's 0 out of 6. So 0%. The next one. 100%. All the numbers we have in our sample space, they all are bigger than 0. 1, 2, 3, 4, 5, 6. So it's 6 out of 6, which is 1. It means the 100% guarantee that when you roll a die, you'll get a number that is bigger than 0. Okay, any question? Great, let's see next. Answers. Do you need a moment to copy this down? You do? Then let me take attendance for the day. I prefer fraction because I don't have to do any math. Today is 9:16. Allison, not here. Danielle, Eloise, Yasmin, Ryan, Janae, Anton, Christina, Ninichi, Christopher, said he'll be here today. Come on. Miyako, no, Ramis, Jamina, not here. Waiting. Xian, close your laptop. No laptop in class. No tablet unless you're right. Unless you use it to write. Tao, Lila, Jason Lu, Jason, Yusuf, Christabella, Nithya, yeah. Kevin, Salma, Keith, Karina here, Maria, Mia, Tahmina, oh, Karina, Wendy, Sebastian, Fatima, Tanvir, absent. Ivanov, absent. Oops, sorry. Queenie, Jason Ju. Okay, let's see what we have next. If a test has 3 true-false example, sorry, true false multiple choice, then what are the outcomes you can get? You're taking an exam and it has 3 true-false questions. How many words you can pick? Something true, something false. Tree diagram means tell me all the branches. Okay, so this is question 1. This is question 2. And we have one more question. So each will have more branches. So true, false, true, false, true, false, true, false. And now we are going for all the things we have in the sample space. What's the first one? True, true, true. Tell me the second one. True, true, false. Next one. True, false, true. Then true, false, false. Huh? What? My. Oh. So this is this. And this is this. True, false, true, true. Let me highlight it, easier to see. Okay, the next one. False, true, false. Then false, false, true. And finally, false, false, false. If you can do it in your head, you don't need the tree diagram. But if you know how to use a tree diagram, it will be easier. What is the probability that you're so unlucky? Everything you chose was false. One out of 8. Wonderful. It says all of them are false. So false, false, false. How many false, false, false we have? Out of total, how many are found? 8. It's 1 out of 8. What's the probability that exactly 2 true? Right. 2 out of 8. Let's check. Exactly 2. We have one of them here, one of them here, one here. How'd you get 2 out of 8? False. 3 out of 8. It's just exactly 2. So the second one, third one, and in the false bunch. Was there any confusion for these 2 questions? Is all of you are okay? What's the probability that at least one true? It's the same thing. Wonderful, it is true. At least one. It means it could be 1, it could be 2, or it could be 0. So if you check all of these, there is only one thing which doesn't have any true. This one. Except for that, everything has true. So when we talk about at least something, there is actually another way we can calculate that. We can use this complement. It means 1 minus no true. Sorry, probability of no true. Probability of no true means all false, right? So 1 minus probability of all false. So there is exactly 1 we have that has no true, all false, 1, 8. So 1 minus 1, 8 is 7, 8. So sometimes actually we need to use the complement. When we have a big numbers to work with, we cannot possibly draw all possible outcomes. So that time we have to use complement. Because complement is always, not always, usually a small number. Okay, the next one. probability that at most 2 false. 1/2. So 4 out of 8. At most 2 false. 6 out of 8. What did you say again? 3 out of 8. Okay, so you change the number from 4 to 3. How about you, Nitya? 7 out of 8. 7 out of 8. Any other guesses? I'll see with the winner. Okay, at the most 2. In at most 2, how can you represent that using inequality? Probability of false. 2. So how do you tell, like, this one or this one? Which one? Bigger than or equal or less than or equal? At most less than or equal, right? So we can have everything less than 2, including 2, right? Less than 2 means we have either 0 false, 1 false, or 2 false. So how many choices we have here? Either 0 false, 1 false, or 2 false. How many of them satisfy this condition? 7 of them. This has 0 false. This has 1 false. 1, 2, 1, 2, 1. So 2. Why we cannot use this one? It has 3 false. So it cannot be the last one. That means the winner is actually 7 out of 8. So did I run? Or you can actually use the complement. 1 minus 1, because 1 minus 3. At most 2 means 1 minus 3 false. 1 minus 1 is. Any question? In true, how many false you have? You must count 0. So at most 2 means either 0, 1, or 2. 3 of them. These 2 are tricky. So 1377. Do you have it? Yep, 1377. Okay. So far, how are you feeling about probability? Not bad, right? Great. Can you quit? Now, so these are classical approach. You think logically, either using your brain or some type of figure or whatever is easier for you. Relative frequency, we're going to have some type of table, and you're going to count the frequency divided by total we have. So it's number of observed or number of times some events can occur divided by total number of repeats or trials. For example, if 20 of the 150 randomly selected computers are made in a factory and defective, what's the probability that the next computer made is defective? So you want to see what is the probability that our next computer we are making will not work. We know that every 20 out of 150 doesn't work and don't work. So what's the probability that the next one they are making will not work again? Anyone else? Yeah. Let's give them a chance. Promise, I jumped. So what over what? True. Nitya, do you have the same thing? Exactly. They actually gave us the frequency. 20 in every 150 doesn't work. So the probability that the next one will not work is 20 out of 150. We didn't have to take math. They just gave us the math. They just gave us everything. Just to put one over another one. And then simplify. So 2 out of 15. The next one is not a question, just an example. If you flip a coin 100 times, flipping, the amount of times a head actually did appear would be the relative frequency. So if there were 59 heads and 41 tails, the relative frequency of flipping a head is that 59 out of 100. Then what would be the probability of tail? Good job, 41 out of 100. So relative frequency is the easiest one. They give us all the information, we just have to see what do you have to put. Sure, what is confusing, like which part? They're saying you're flipping a coin 100 times. And suppose when you're flipping 100 times, 59 times you got head and 41 times you got tail. Now they're asking what is the probability of getting head? 59 out of the 100. Now another table frequency probability. They gave us a table and we just have to observe and collect the information. So we have number of rows and total number of sixes. So you are rolling a die 10 times, 20 times, 30 times, 40 times, 50 times, and you're counting how many times we see 6. So when you roll 10 times, you see 6 twice. When you roll 20 times, you see 6 3 times. When you roll 30 times, you see 6 times. Okay, this is what it means. Number of times you're rolling and number of times you see 6 in those many rolls. Now, what is the probability of getting a 6 in the first 20 rolls? So you're rolling 20 times. What's the probability of getting a 6? 0 over 20. So it says getting a 6 in first 20 rolls. This is our 20 rolls. And we can see in a 20 roll, 6 usually appears 3 times. What's the probability of getting 6 in first 50 rolls? This is our 50, and this is how many times we see. So it's 9 out of 50. Cool, right? We're not using our brain, we're just using our eyes. These are the answers. And now subjective approach, the least accurate one. Subjective probability is where you use opinion to find probabilities. No calculations are involved. Usually, no calculations are involved. And it involves your opinion, your experience, your beliefs, those things. A probability of 1 represents a belief that the outcome will certainly occur. A probability of 0 represents belief that the outcome will certainly not occur. Example. An individual who believes that there is a 70 chance that it will an individual who believes that there is a 70% chance that it will rain tomorrow. So I'm missing a rain. I should fix this. It will rain tomorrow. He is using the subjective probability. Another person may think there is 20% of probability of raining tomorrow. So it's his belief. So if you are not an weatherman or weatherwoman, and you're guessing, oh, I think there's a 50% chance tomorrow it will rain. That means using subjective probability. Usually my sister does that. She look at the sky at night, and the sky is white. She said, oh, tomorrow it will rain. And if it's blue, she's like, oh, tomorrow it will be very sunny. So without any weather knowledge or anything, she just use her experience and guess what will happen tomorrow. Sometimes it works, sometimes it doesn't. The second one, if you study all the questions very well, what I tell you to study, again I forgot to put the review sheet, I'm going to do it. So there's a 99% chance that you'll ace the exam. That's my belief. Okay? Sometimes it works, sometimes it doesn't. When it doesn't, do you know why it doesn't work? Can anyone guess? You studied everything very well, but still it didn't do well in the exam. One reason, you didn't take the exam. Good. That means overloading. So what happens then? True. Another word is examophobia. You know everything very well, but when you're taking the exam, it just blank out. See? That didn't help. So it's not actually true always. If you study and remember until after the exam, after you take the exam, then you waste the exam. I cannot say until the exam. What if during the exam you forget? See? So until after the exam, if you can remember, after studying all the materials, then it's a guarantee 99% that you ace the exam. Okay, so we have three approaches. When do we use which one? The classical approach is appropriate only for modeling experiments with equally likely outcomes. Do you remember this expression, equally likely? This is the second time I'm mentioning it. What does equally likely means?
They're like independent events that are going to occur in this particular weather. So you have a chance of getting any of them. And
they all have the same chance of that.
yes.
There is one error in the answer independent. They are not. Sometimes they are, sometimes they are not. So equally likely means every outcome has equal chance of being selected. For example, when you roll a die, we have six outcomes, and all of them have same probability, 1 out of 6. So they are equally likely. When you flip a coin, two sides, they have the same probability. If you flip a fair coin, did you guys know that there are some coins that are not fair? I didn't know that until I took probability. So yeah, if you flip a fair coin, then getting a number of head and getting a number of tail, they have the same probability. So these are equally likely. Relative frequency is useful when you do an estimate based on observing the outcomes of the experiment. And subjective, anywhere else. If you want to boost, oh, I know something, make a guess, something like that. You can use anywhere. It's a personal belief. Like my sister, oh, tomorrow it will rain, like that. Okay. Basic rules, probability is always a positive number, and it's always a fraction or 0 or 1. Okay, so it could be only two whole numbers, 0 and 1. Besides 0 and 1, none of the probability can be a whole number. They have to be a fraction lying between 0 and 1. You cannot have probability more than 1 or less than 0. And when you add all the probabilities in the sample space, the result is 0. For example, probability of head plus probability of tail, when you add, the result has to be 1. It's true, right? Probability of head is 1/2, tail is another 1/2, 1/2 plus 1/2 is 1. So when you add the probabilities for all sample space, the result is 1, and probability cannot be negative or bigger than 1. not about complement. If you add an event with its complement, the result is 1. Complement means something that doesn't happen. So if probability of head is our event, then probability of not having an head is our complement. In other words, getting a probability of tail. So when we add the two together, it's 1. If we solve for 1, all we have to do is subtract the other one from 1. So if you want to find probability of your event, it's 1 minus the complement. If you want to find what the probability of the complement, it's 1 minus the event. And two events are disjoint or mutually exclusive. Disjoint means they are not joined together. They are separated. One is not connected to the other one. Two events are mutually exclusive. If two events are mutually exclusive, then probability of happening either one of the events is the individual sum of the individual probabilities. The probability of happening E or F means add the probability of E with the probability of F. These are basic rules of probability. And guess what? These are good exam questions. True false, multiple choice type. So you may see these all 4. I may put one of the rules and say this is true or false, or I may put it as a blank. Like probability of event not E is what? It's 1 minus probability of E. Any questions so far? Huh? October 8th? Right?
Yeah.
October 8th? Yeah. So we'll see whatever we finish before October 8th or as a whole based on that. But my plan is to do at least chapter 7 to 8. Finish chapter 7 or 8 before exam. So exam 1 will be from chapter 1 to 8. So. But see, I'm going very slow, right? So I'm not sure how much we can finish before that. Okay, complement, I already described. Complement is something not happening. Example of complements, if your event A is getting a number odd when you roll a die, its complement is getting a number even when you roll the die. So complement is not the event itself. Complement of an event A is everything else in the sample space that is not in A. You know, there are a few types of complements. I mean, when you write, one complement is with E, another complement is with I, right? Well, what is what? What is with I and what is with E? Maybe E is complement here, something not open. Then I means what? Giving you complement? Huh? I always get confused. Which one is what? Which one is E and which one is I? Anyway, let's see. Okay, find the complement of this. Selecting a weekday, what would be its complement? Huh? What did you say? Selecting you. I forgot to Weekend. Perfect. A complement is selecting a weekend. So weekday and weekend day, they have nothing in common. They are separate events, so they're complement. How about if the event is roll a die and get a 4? What is its complement? Not getting a 4. What is the complement of passing this pass? Failing the pass. See, you got the idea very well. Complement. Now, I think this is from your homework. Suppose the probability that a college student who has not received a flu shot but he will get it is 0.45. Now, based on this information, what is the probability that he will get the flow chart? What did you say? 0.45, yes, because says we'll get it. Then or not, no. It says who has not received yet, but he's going to get it. Right? Student who has not received a flu shot will get it. So even though you get it is 45. So probability of getting the flu shot is 45.45. Then what's the probability of not getting the flu shot? 0.55. How did you figure that out? 1 minus 0.45. So you see, if you get the flu shot, its complement is don't get the flu shot. So the first one says, well, get the flu shot is 0.45. So not get the flu shot is 1 minus 0.45. Because the complement and the even itself, when you add them, the result has to be 1. So if you want to find one of them, just subtract another one from 1. Just easy, right? Okay. Blah, blah, blah. And this rule is for, this is the rule. That's how we read it. Probability of A or B, that or symbol we represent using the union sign. And probability of A and B, the and is represented by intersection sign, upside down. So you may not see the word or and in math, but mostly you will see them. And sometimes, to make it even more shorter, the A and B simply can be written as AB. So if you see AB, it is A and B. But you cannot write this for U, for OR. For OR, you must use U. But for AND, either use the intersection or don't use anything at all. Okay, so mutually exclusive or disjoint means they are not connected. I don't know, I changed my mind. I changed it somewhere else, but not here. I did another slide before that. But anyway, we're rolling a die once, and let's say the event A is getting a number less than 3. Event B is getting a number bigger than 4. Let's find the sample space. What do we have in the sample space for A? A number less than 3. 1 and 2. And what do we have for this sample space? 5 and 6. Okay. Now, what's the probability of having A or what did you say? 2, 6. 2 over 3. Okay, sorry. 2 over 3. How did you get that? It says or, so let me try to that here. And it is this. Or means probability, or means everything. So if you look at the sample space for A or B, it's 1, 2, 5, 6. The sample space. Now to find the probability, we have 4 in our sample space. 1, 2, 5, 6, 4 elements. And when you roll a die once, total sample space is what? What number you have? 6. So it's 2/3. When you're doing OR, it means you're adding. So anything you see in both elements, you take everything. If you see the same thing twice, just you take it once. Okay? And you take everything for both events. Another example from Kumar, we have a bunch of tiles. When you roll a die twice, the probability of getting something, I don't know. Oh, no. What's the scenario here? What's the probability can you to roll of 3 or 5? Oh, probably this is total. When you roll a die twice, so this is the sum. I missed the direction. This is the sum of 2 dice. So you're rolling 2 dice at the same time. And all these numbers, these are the sum. Sum 2, sum 3, sum 4, sum 5. So you're seeing what number you have on the first die, and on the second die, you add them. Those are the things you get. What's the probability of getting a total, a sum of 3 or 5?
6 over 36, which is 5.
How did you get 6 over 36? What did you do?
5 was 4 over 36. 6 over 36.
Which is 1/6. So getting a sum of 3 has a probability 2/36. Getting a probability 4, 35. That's what I'm saying. What's this? Getting a 5 is 4 out of 36. And we don't know the numbers, we're just looking at the sums. So we just add them, whatever we get, that's the answer. Good news, I'm not going to give something like this in the exam. I'm going to give you something interesting, but this is from the homework. So that's the good news, it's from the homework. Okay, the next one. Ryan, how did you figure that out?
So probability of we have 36. Probability of getting 5 out of 36. 12 is 1 out of 36. Then you add all that. It's 5 out of 36.
Yep. And if you simplify, 1/4. So you're not doing anything, you're just observing. 4 has a chance 3. 5 has a chance 4. Sorry, why keep making mistakes? 8. 8 has 5 and 12 has 1 out of 36. So add all of their probabilities, whatever you get, that's the answer. Not getting sum of 4 or 8 or 12. How do you know?
Take 1 subtract 1.
Yeah. If you observe B and C, they're actually complement of one another. In B, you're getting the sum. In C, it says don't get the sum. So you have 2 choices. Either you use the table and don't get those, means get everything else except for these 3, add all the results, or 1 minus probability of getting 4 or 8 or 12. So 1 minus 1/4, because you already did it here. That gives us 3 out of 4. Okay. So sometimes complement is much easier to work with than the original setting. So if you do the original setting, you're going to get everything else except for this three highlighted one. And if you don't trust, you can try it. So we add all the numerator and then see what they have when you simplify with the 36. You should get 3/4. Any question on this one? No? Let's see. Venn diagram. These are called Venn diagram. So Venn diagram are the probabilities when you see them visually. Okay, the visualization of probability. So if A is an event, so let's say the function is A. That means everything not in A is the complement. So the orange one is the complement. And second one says, if you combine two events together, A or B, it's the whole thing we have inside A and B. If you see something more than once, count it as once. So everything we have in the event A and B, this we represent by OR. The and thing is whatever they have in common. So this portion, so let's change it to something here. And means what do you see in both A and in B? So this is the and, which is the intersection. And to disjoint event means they are not connected. They are separated from one another. They are disjoint. So how do you know which events are disjoint? Well, easy. All you have to do is look at their intersection. If they don't have an intersection, the intersection is 0, they are disjoint. But if they do have something which is not 0, they're not disjoint. So if you're two events are given, and they want you to figure out whether these two events are disjoint or not, look at if you have any information about their and. If you have probability A and B equals some number, that means it's not disjoint, because the and should be 0 in order to be a disjoint. And means what do we have common in both events? See here, they have nothing in common. So they're disjoint. So that's how we figure them out. Why do you care about this? Well, because based on the events, whether they're disjoint or not, we have two rules for addition. If you have disjoint events and they want me to find or probability of A or B, then your formula is probability of A plus probability of B. It means here, if they want to find the probability of A or B, you have to find probability of A plus probability of B. We don't have anything in common, so it's simply the sum of the individual probabilities. However, if they're not disjoint, means there's something connected. So that time, the addition rule is the individual probabilities minus whatever portion they have in common. So you must subtract this common portion from the sum of the individual probabilities. They don't have any common portions, so you have nothing to subtract here. But in these events, they have something in common, so you just subtract it. That's why, depending on what type of events you're working with, the same rule, but they have two different views, two different ways of writing. Clear? You should write all of this down in your cheat sheet. Did they say that you are not in the cheat sheet in that one? So in your exam, you will have a one-sided cheat sheet. In the cheat sheet, you can use all the formulas you learn in this class or all the important things you learn. Okay, so we have all the background knowledge. Now let's apply the probability of getting a number greater than 3 or odd number when you roll the die. What is the probability? What's the probability of getting a number bigger than 3 or an odd number when you roll the die once? Let's say getting a 3, so getting a number bigger than 3 is your event A, and getting an odd number is your event B. There are two events here, right? Getting a number bigger than 3 and getting an odd number. And it says or, so probability of A or B means probability of A union B. 5/6. How did you figure that out? So event A, what's the sample space? Sample space 4, 5, 6, and event B, what's the sample space? 1, 3, 5. From here, what's the probability of A? 3/6. Probability of B, 3/6. Do they have anything in common? What do you see? 5. So from here, probability of A and B is what? 1/6. So that means to find this out, we can already see that they are not mutually exclusive. So when they're not mutually exclusive, this is our formula. Take probability of A and probability of B. But since they have something in common, erase this part. Sorry, delete this part or whatever. Get rid of this part. Probability of A and B. So we have 3, 6, another 3, 6, and then 1, 6. That gives us 5, 6. See, a very nice example of not mutual exclusive. They didn't tell us whether it's mutual exclusive or not. We figured them out by observing their sample space. So since you're a beginner, you can actually do this way. For every event, write down their sample space. And then you can see whether they're disjoint or not disjoint by observing the sample space. Was it confusing for anyone? Anyone needs more explanation? No. I love this question. You may see this in the exam. No question? Do you see the sample space here? We have 4, 5, 6, and 1, 3, 5. Do you see any number common in both sample space? How many numbers you see in common? Out of total, how many numbers? So A and B means you have both A and also in B. So in short, what you learned is that if you have disjoint events, you need to subtract their joint portion. If you don't have disjoint events, you have nothing to subtract, just individual you add the individual probabilities. Now let's do another example. A more realistic one.
Sorry, over. Sorry. Is it like 3, 6?
It's mine as a mine. Thank you for catching it. Suppose the class record shows that 80% of the students need to work in math. 70% need to work in English. And 55% need to work in both math and English. Are these events need math and need English mutually exclusive? If you want, you can drag them down. Just by reading this, what do you think? The event need math and the event needs English. No? Why not? How do you know they are not mutually exclusive? What hint do you have? See, both means A and B. We do have a number for A and B. But see, the rule to figure out which events are disjoint and which are not is that two events are disjoint if we don't have anything common, anything for and portion. But here we do have an and portion. So let's draw the Venn diagram. It says, okay, let's say this is math, this is English. It says 55% need both. Right? What do we write below M for the math portion? What percentage? 25. How did you figure this out? So we have total 80. And from this 80, we have 55 in here. That means we have left with 25 on the other side. Then how about English? What number we put after English? Below English. 15. So we have 70 total, but only that portion is 55. So we're left with another 15 on the other side. So if we add all of those, what number we have? 25, 55, 15. Total, how much we have? 95? Okay. Could be. What happened to the 5%? Remember I said when you add all the probabilities, they have to add up to 100%. So what happened to our extra 5%? Good job. It's a compliment. This portion need help in math. This portion need help in English. Total 95% they need help either in math or English. But there are 5%, they're so smart. They don't need any help. So they're invisible 5. Okay, what is the probability that the student needs math or English? Huh? Say it louder. Huh? 40. How did you figure that out? It says math or English. True. So we have or And we know they're not mutually exclusive, so I need to subtract and portion. Probability of A or B is probability of A plus probability of B, and we are subtracting the common portion, A and B. A is 80%, B is 70%, and we have 55 in middle. So total, what do we have? 40? 95, it should be 95. Because or means everything. We have here. And this is 95. How'd you get 40?
Like they need both.
You add method English, that's a sum. And then you subtract how many of them need in both. Help in both.
So or means everything and then add what's happening.
And means, yeah, only that small portion. So we actually didn't need to do any math here. If you draw your Venn diagram and you collect the total here. That's what I was thinking, like 40% how?
But I also think, I think we can use an inclusive or, which is, we're just like this or this, no, this and not to the.
Math is confusing.
It's too.
Equality or means take everything, and if you see the same thing twice, it is don't take that twice, take it only once. So subtract the portion you see twice. So we see this portion twice, once in math and once in English. Since we see it twice, so you subtract once. So you subtract the 55 and we keep once here. Okay. So this is also one of my favorite. Who knows? Maybe you'll see this in the final exam. So you should write exam. I don't make the final. But sometimes actually this question come in the final. Exam. Think about it for a second. What's the probability of selecting a boy on a weekend? At first, or it's like, it doesn't make any sense, right? Why it doesn't make any sense? Or I should ask, what type of events you are working with? Right? So, do they have something in common? So, which type of events they are? Joint or disjoint? So, what is the formula for disjoint or rules? Or for the disjoint? So, probability of boy plus probability of weekend. We have nothing to subtract. We have nothing in common. Now the interesting question. What is the probability of getting abortion? In normal case, yes. But how about you have a twin? It's more complicated, right? And some people have 6 children at the same time. What do you call them? Quadruple? No. 4 is quadruple, right? And 6 of them, what do you call them? Sextuple? Sextuple? See? This rule doesn't apply to those people. There, yeah. How about the weekend? What is the probability of selecting a weekend? 2 out of what? 7. See, they have totally different denominator, totally different, two different worlds. But see, it's an example of not, it's an example of disjoint events. And do you know how do you add them without using calculator? What is the common denominator? 14.
Plus.
Mm-hmm. We can get the numerator by multiplying this plus that. 7 plus 4 gives us what? 11 out of 14. Why are you wasting our time? It doesn't make any sense, right? Why do you care about weekend and boy or girl? Unless you care. But some people do care. Like they want to have their baby on a specific date, right? So they try their best to give back their baby to that date. It happens sometimes, but sometimes not. Life doesn't always go as planned. Why is everybody fun? See, when you have fun, time flies. So goodbye, everyone. See you again online on Wednesday. And you're going to do more fun examples. And again, I extended the homework take for two more nights to make sure you finish all the homework before Wednesday. Or by Wednesday night, actually.